we're going to create a special kind of series, and we're going to use the integral test to give us information. It's called a p-series, and it looks like this. Series, as n goes from 1 to infinity, it's 1 over n, where p is a number. So it's n to the p power. So in this case, p is going to be some number. So clearly this is a perfect setup because we can say f of x is 1 over x to the p, which is x to the negative p power. So I'll be able to use the integral test to do this particular series. And what's going to happen is we're going to use the integral test, and it's going to tell us for what values of p this would converge or diverge. So we set up the integral from 1 to infinity 1 over x to the p dx, which is the integral from 1 to infinity x to the negative p dx. So now this involves, of course, my limits. So it's the limit b approaches infinity 1 to b x to the negative p dx. The antiderivative of x to the negative p is x to the negative p plus 1 over negative p plus 1. So we get limit b approaches infinity, x to the negative p plus 1 over negative p plus 1, evaluated from 1 to b. We get limit b approaches infinity, b to the negative p plus 1 over negative p plus 1 minus, plugging a 1, we get 1 to anything is 1 over negative p plus 1. And looking at this, we can see that negative p plus 1, we can't let that be 0, so certainly we're not going to be able to let p equal 1. So p cannot equal 1. Now we can see when we put in infinity, it's going to all hinge on whether the exponent, negative p plus 1, is positive, which would keep infinity on top, or negative, which would put infinity on the bottom. So we have to do these in cases. So let's take case 1. In case 1, negative p plus 1 is positive, greater than 0. So negative p is greater than negative 1, dividing by negative 1. That means when p is less than 1, we've got, as we said, a positive exponent. So the limit as b approaches infinity, b to the negative p plus 1 over negative p plus 1 minus 1 over negative p plus 1 will be infinity to a positive. So basically it'll be infinity, which diverges. Remember that this is a positive power when p is less than 1. So it's infinity to a positive, which keeps infinity as the answer. Now the other case will be if the exponent is negative. So case 2 will be negative p plus 1 is less than 0. Negative p, putting the negative 1 here, is less than negative 1, which means p is greater than 1. Then we're dealing with the limit as b approaches infinity, b to the negative p plus 1 over negative p plus 1 minus this. But this exponent is negative, so I'm going to be able to write it as 1 over and change it to a positive. So it will become the limit as b approaches infinity, 1 over b. The opposite of negative p plus 1 is p minus 1, and then we have negative p plus 1 minus 1 over, we've got this negative p plus 1. Now we've got 1 over infinity, which gives us a 0. So this limit is negative 1 over negative p plus 1. It converges. The last remaining case, of course, goes back to when p equaled 1. So our series 1 to infinity, 1 over n to the p, becomes the series 1 over n, which is a very important series. It has a special name. It's called the harmonic series. For this one, I have to do the integral test separately. 1 to infinity 1 over x, which is the limit b approaches infinity, integral 1 to b, 1 over x dx. But that antiderivative is natural log. So it's the limit b approaches infinity, log absolute value of x from 1 to b. So it is the limit b approaches infinity, log b. I don't need the absolute value because b is going to positive infinity, minus log 1. Log 1 is 0, but the log of b as b goes to infinity is infinity, so it diverges. So now we'll go to the next page and we'll summarize what we just did. We started with a special kind of series from 1 to infinity, 1 over n to the p power, where p is a real number. And our result was when p was less than 1, that series diverges. Also, when p was equal to 1, the series diverges. So we'll remember it as p less than or equal to 1 diverging. The other result was when p was greater than 1, that's when we had the series converging. And we're going to memorize this because it's going to be very useful going forward, especially with the comparison test.